Hey Phys 1 kids, Campbell here. In our second last video on the forces unit, we're going to talk about problems with pulleys. Now, a little background first is, when we have a pulley, we have rope or string, and we're going to deal with massless strings because then the force is transmitted through the rope. So the force at one end of the rope is the same as the force at the other end of the rope. And so all that rope does is transmit the forces. And so one thing you should know is that the tension is the same everywhere in the rope. So if I have a rope and I pull on one end with 4 newtons, then the other side is being pulled on with 4 newtons. And in the center of the rope, the tension force is 4 newtons. It's not 8, even if we're both pulling with 4 newtons. Now, all a pulley does is change the direction of the tension force. It doesn't affect it at all, especially because we're going to deal with massless, frictionless, ideal pulleys. Physics fantasy land, man. Massless strings and ideal pulleys. So that means that the pulley is not going to have any effect on the force of tension. It's just going to change the angle at which that force of tension is applied. Now, a couple properties of pulleys. Because the pulley only redirects the tension force, that means that when we draw free body diagrams, the tension in the rope connecting each of the objects is going to be the same. Think of it like a Newton third law pair. So like here I have this guy, he's climbing a rope that's attached to a weight here. And so if I drew a free body diagram of it, here would be the man, and that force vector would be the weight of the man, or the force of the gravity of the earth on the man. And here would be the tension force of the rope on the man. Well, all this pulley is doing is redirecting the tension force, and since the tension force is the same everywhere in a rope, when I draw a free body diagram for this, maybe it's a sandbag, I don't know why it's called S. But we have our free body diagram here, separate free body diagram for this object, and we have the weight of the object down, and we have this tension force, right, because the rope is attached to the box or the sandbag or whatever this is, up. And by the effect of pulleys, these tension forces are the same in magnitude. Notice they're same in the direction in this case. All the pulley is doing is just redirecting that tension force. So think of this as a Newton third law pair, equal but opposite, although they're both pointing up, but equal force vectors. Now, the other thing that's really important to know about pulleys is if there's acceleration with a pulley, because they're attached, they have to move together, right? If you tie yourself with a rope and you attach it to a friend, right? When they accelerate, you accelerate. They kind of drag you along. So your accelerations are the same. The thing that will mess you up, though, is, for example, in this picture, they show that this guy's accelerating up. The acceleration of the man, it's positive, whereas the bag is accelerating down. So the acceleration of this bag, or whatever this is negative. But the acceleration of the man is equal to, but opposite of, the acceleration of the sandbag. So again, tension forces are equal. The accelerations are equal, but they have opposite signs because one's always going to be up and one's going to be down. Now, let's take a look at a problem. I have a force that's I'm holding this crate up. Don't ask me why, but I am, and I'm good at it. And I want to know, what is the force that I have to apply to this string? I don't think it's really a string if it's 45 kilogram mass. I'm thinking more like a rope. But what force do I have to apply to this rope? Well, let's draw a free body diagram. All right, I want to know about the force I'm applying to the rope. So if I draw a free body diagram for me, all right, we would have the force I'm applying. We're not going to worry about the weight of my hand, but the force I'm applying and my force of tension up. Well, to find out the force I'm applying, then I need to know what the force of tension. Well, where is that force of tension coming from? Why is there tension? Well, it comes from the crate. So I have to draw a free body diagram of the crate also. So, of course, my crate has a mass, so we need to pay attention to that. So I have the force of gravity of the crate down. and I have the force of tension up. And by the property of pulleys, that force of tension on the crate has to be equal of the force of tension of my hand. So we'll call that crate, we'll call that hand. Well, first let's find out, and if I'm suspending, right, that suggests that I'm at rest. So that means I'm going to use Newton's first law that says the sum of the forces has to equal 0. All right, well, where do I got numbers? I have them over here. So I know that the force of tension on the crate is up. And so the force of gravity is down, so Fg. And that has to equal 0. So the force of tension on the crate has to equal the force of gravity. And we know that the equation for force of gravity is mass times acceleration due to gravity. So the force of tension in the crate is equal to the mass, 45, times the acceleration due to gravity, 9.8, which gives me a force of 441 newtons. So that's the force of tension in the crate. And so now if we go to our free body diagram for my hand, right, we have the force of tension from my hand up minus the force applied, and that has to equal 0. So the force that I'm applying has to equal the force of tension from my hand, from that rope, which, because the tension is the same everywhere in the rope, has to equal the force of tension in the crate, which means it has to equal 441 newtons. So these tension forces are the same. The force of tension in a rope is the same everywhere. All a pulley does is just redirect that tension force. Let's take a look at a problem where there's acceleration, because this is where you're going to make some errors. So if I have two masses hanging by a rope across a pulley, and let's say that mass 1 here is 7 kilograms, and why does it keep doing that? 7 kilograms, and mass 2 here is 12 kilograms. So if I do this, if I hang these masses that are different and I let go, what's going to happen? Well, we're going to have this mass accelerate down, right? And we're going to have this mass accelerate up. So there's my acceleration, right? The heavier one is going to pull the lighter one. Now, a couple things to remember. Tension is the same everywhere in the rope. The acceleration values are also equal, but in opposite directions. So first, let's make some free body diagrams here. So we have here our force of gravity from block 1 down and our force of tension on block 1 up. And we know that this block, so I'm going to write off to the side and never put this on a free body diagram, but if you write it off to the side, it might help you remember that this one is accelerating up with positive acceleration, which means I must have a net force up. If we go to our second block, our 12 kilogram block, right, we also have the same sort of free body diagram. We have that force of gravity down for block 2, and we have our force of tension, it's supposed to be a force of tension up. But this one, because this mass is heavier, it's going to be accelerating down, right? So that's a negative acceleration. Very important to remember that, right? Negatives have a big impact in math. Now, these are accelerating, so I'm going to use Newton's second law, sum of the forces equal mass times acceleration. But I need to do this for both block 1 and I need to do this for block 2. You can't, let's not combine these. So this will be mass of block 1, mass of block 2 into one equation. Now we could treat them as a system and do that, but we're not going to do that. We're going to treat them separate. All right, so let's go to block 1, right? This is my block 1, and we look at our free body diagram and we see that we have a force of tension that's vertical up, so that's positive, minus the force of gravity of block 1 down. Again, sorry about that. And that's equal to mass 1 times its acceleration. Let's keep going here. I can plug some more stuff in here. Force of tension here. Force of gravity of block 1 would be mass 1 times g, and that's equal to m1a. And I can solve this for force of tension. So I get force of tension is equal to m1a plus m1g. Woo! How exciting. All right, let's do the same thing for block 2. Same equation, right? Force of tension up, vertically up. the force of gravity is down, so minus F, force of gravity for 2, and that's equal to m2 times a negative a. Don't forget that this has a negative acceleration. It's going down. Big difference, right? If you forget the negative a, then this equation is going to look exactly like the other one, and it shouldn't. All right, so we got force of tension minus m2g, right? That's the force of gravity equation, and I'm going to pull this negative out, so we're going to put m2a. Okay. Let's rearrange and solve for force of tension. Force of tension is equal to our negative m2a plus m2g. All right. Now remember that the force of tensions are the same. So that means that this equation here has to be equal to this equation here. Now notice I haven't put numbers in yet. I'm working in variables. We can plug numbers in later. But seeing the variables will give us a process that we can use every single time we solve a pulley problem where we have blocks that are both vertical like this. All right, so force of tension is the same, right? Tension is the same everywhere in the rope. So that means that m1a plus m1g is equal to a negative m2a plus m2g. All right, let's start moving stuff so that they're all on the same side. Let's put the a's on one side and we'll put the g's on the other side. All right, so I'm going to move this a over to this side. So we're going to add m2a to both sides. And we're going to get m1a plus m2a. And then I'm also going to move this m1g over. All right, so subtract it from both sides. And so that's going to give me an m2g minus m1g. Hopefully you're still with me. So I'm just rearranging the equations to put the a's on one side and the g's on the other side. All right, now let's simplify this. Let's pull the m's out. And so that we have a times m1 plus m2. So I'm just factoring that a out. Same thing over here. I'm going to factor the g out, and I get m2 minus m1. All right, now we're going to solve for a. Ooh, that's supposed to be an a. Ugh! At the bottom of the screen here, having struggles. A is equal to our g times m2 minus m1 all over m1 plus m2. Now, this is one thing that's very important. If we had forgotten the negative, then the term we have on the top here, our m2 minus m1, would be the same as the term we have down on the bottom here, right? Because then I wouldn't be adding this m2a here to this side. So one thing I always like to say is you always add a's and you always subtract the g's. You always add the a's, you always subtract the g's. Because if we had subtracted the a's, right, this term would cancel and it would say that the acceleration of these blocks is equal to g. So if you ever get in a situation where you get a equals g in a pulley problem, you forgot your negative. Because unless we cut these ropes, this thing is not accelerating at negative 9.8 meters per second. All right, now that we have our general equation, let's plug our numbers in. All right, so a is equal to g, right, which is our 9.8, come on, 9.8 times m2, remember m2 is 12, minus 7 divided by the quantity 12 plus 7. 12 plus 7, struggles. All right, if we do the math, we're going to end up with a value of 2.6 meters per second squared. Now, that is the absolute value of the acceleration because, well, or the acceleration of the 7 kilograms, right, is 2.6 meters per second squared. And the acceleration of the 12 is a negative 2.6 meters per second squared. Now, I will tell you, I've had kids memorize this equation because it was a lot of stuff to write down before we got there. And that is totally cool to memorize it. But you need to be able to apply it. So what I want you to do now is I want you to try this problem. Now I don't have two verticals. I have a horizontal and a vertical.